Okay, perfect, thank you. Can everyone hear me okay? Brilliant, and sorry about the slight delay. I'm actually on a Linux and there was a bit of an issue with the display, so that's just one example of how we Linux people tend to annoy others, but hopefully we'll make a start now. So my presentation is based on anomalies, specifically outliers, time series shocks, the issues that we can sometimes face when we are working with these type of anomalies and how we can solve them. So to start off with, a little bit about myself. I am a data science consultant and educator based in Ireland. I work primarily with Python and R, and I work with statistics, which is primarily what we're going to be covering in this presentation here, but also with things like machine learning, so Keras, scikit-learn, etc. So to start off with, how many of you have had this problem before? You get a data set from whatever you're working on, and you have certain observations or certain outliers that are completely out of the mean, that are completely different from the rest of your data, and it causes all sorts of problems. How many of you faced that issue before? Yeah, I see many hands going up, so it's not just me. So outliers can be a bit of an issue because it skews our data, and essentially when we are trying to forecast or we are trying to use regression analysis, machine learning, what have you, to try and come up with valuable insights, outliers are usually a significant impediment when it comes to doing that. And the two recommended courses of action that we usually face are either get rid of the outliers or transform the data in some way. So transform the data into a normal distribution, for example, and see if that can fix things. Now, neither method is necessarily ideal, because when we do that, we're either removing valuable data in the first instance, or we are changing the data in such a way where we're also losing valuable information because we're not necessarily accounting for the fact that this data is different and shouldn't necessarily be normalized. So just as an example, if you consider the following array of numbers, so we have 5, 8, 10, 10, 15, and 20. So we calculate our mean, we calculate our standard deviation. Now we add one number to the array, in this case 1,000, and we see that our mean and our standard deviation have deviated dramatically. So if we're trying to generate an analysis, it means that the shape of our distribution is going to have changed. And if the shape of our distribution has changed, that's going to affect the types of models we're going to run and the validity of those models. So I'm sure all of you have heard of a normal distribution, a distribution where we have the mean equal to the median, equal to the mode, and we have a symmetric bell curve. Now, hands up if you think yes to this. Hands up if you think we need a normal distribution to run regression analysis. Hands up if you think we don't. Hands up if you haven't got a clue. Okay, so I see more hands for the third option. But anyway, the long and the short of it is, it's a common misconception that we need a normal distribution. We don't necessarily to run a regression analysis. But that doesn't take away from the fact that when we generate a distribution, if we have significant outliers, as you can see in this case, you can see just a tiny little bar between 70 to 80,000 on the right, you can see that this has heavily skewed our distribution, and in this case we have a heavy right-tailed distribution. So, as I mentioned, we don't need a normal distribution when we run regression analysis, so all we simply need is that we have a blue estimator, or in other words, a best linear unbiased estimator. However, like I said, outliers significantly change the shape of our distribution and hence the overall results that we can get from that. So outliers, essentially, the three main things to bear in mind about them: they can skew our mean and standard deviation, they can affect our significance readings when we generate regression analysis. So for example, it increases the possibility of a type 1 or a type 2 error. In other words, rejecting a true null hypothesis or accepting a false null hypothesis. So, once again, the usual courses of action that people take are either removing the outliers, normalizing all of the data, or keeping the outliers, and neither of these situations are ideal because it risks skewing the regression results. Now, there is another solution to this, and can anyone think of what that might be? Yep. You're getting there. So when you say replace, what we don't want to do necessarily is replace the actual observations. Instead, we want to come up with a weighting mechanism. In other words, if we have extreme data, we want to be able to come up with a mechanism whereby we place less emphasis on the extreme values and more emphasis on values that fall closer to the mean. So what we're going to be looking at is what's called a robust regression. Regressions, in other words, that adjust the weights of our observations in order to be able to come up with a better analysis. And the two types of regressions we'll look at are the Huber and the bi-square regression. So in terms of a linear regression, which is most commonly an ordinary least squares regression, when we run this type of regression, what we're trying to do is we're trying to minimize the sum of the squared residuals. In other words, we're trying to minimize the distance between our predictions and the actual values. Now, if significant outliers are present, what tends to happen is that least squares become too sensitive to extreme values. So if we have extreme values, least squares become too sensitive to this and it affects our overall results. So what we want to do is we want to run a robust regression. So outliers with extreme values that are measured in terms of leverage. So if we have a high distance between a predictor and the actual value, then we say that this has a high leverage. However, if the distance between the predictor and its actual observation is small, then it has a low leverage. So when we talk about adjusting the weights to give less emphasis on extreme values, we're doing this using a process known as iteratively reweighted least squares. So when we come up with a robust regression, we're coming up with a regression that is insensitive to small deviations from the mean, while at the same time not being overly sensitive to large deviations from the mean. And specifically, what we're using in a robust regression is what's called M estimation. So we're coming up with an M estimator, and we want to minimize rho, which is related to the likelihood function for the residual distribution. And in terms of how do we know whether we can actually class an observation as an outlier? So for example, if I go back to, if I go down to this graph here, for example, you can see that we have many observations at the bottom, and then we have 3 observations at the top, which is clearly distinct from the rest of our observations. But even though we can look at a graph, we don't necessarily know if these outliers are significant. We had a presentation earlier today where, you know, as human beings, we're not necessarily that good at interpreting visualizations. So we want a mechanism to be able to know whether these outliers are actually significant. And the way we do that is by using what's called Cook's distance. So we can come up with a mechanism whereby Cook's distance is measuring whether an outlier is actually significant. And as a rule of thumb, if we have a distance of 3 times greater than the mean, this indicates that we have an outlier present, and this would warrant further investigation. So what I'm going to do is I'm going to go into R, and I'm going to show you up close exactly how this analysis would play out. So our case study is going to be a hypothetical telecommunications firm, and essentially what this firm wants to do is determine internet consumption per month in megabytes across its customers. So there's going to be a presence of significant outliers in this data set that could skew our results, and you're going to see how we use weighting techniques to deal with this issue. So I'm just going to load up my code here, just bear with me. Okay, so this is our data set, and we have our dependent variable usage. So this is the megabytes per month that each individual consumer consumes every month. And then we have things like income, the number of video hours, the number of web pages accessed, the person's gender, their age, etc., in an attempt to form a regression analysis and see, well, can these variables actually determine how much data a particular person is going to consume? And you can see when we sort usage in descending order, we have 3 observations where we have very high usage, and then usage drops off dramatically after the 3rd observation. So we have 3 significant outliers here. So if we look at our summary statistics, you can see that the mean usage, 11,841, and then the maximum, 85,970, which is clearly well beyond the mean. So what we can do, we can split our data into training and test data. So we'll train on the training data and then validate our results against the test data. And when we plot Cook's distance, you can see that we have our 3 observations here that are beyond the mean. And if we go for a QQ plot, you can see that it's not normally distributed by and large, but we have various observations from the quantiles -1 to 1 that fall on the regression line. And then we have 3 observations that clearly are beyond the regression line. They're clear outliers, and they clearly are beyond what the rest of the data is in relation to. So when we plot our residuals, we see that we have the residuals versus the fitted residuals. And we have our QQ plot once again. But this is the graph that we're particularly interested in. So we have Cook's distance here, but we have our outliers, and we have a mechanism for being able to use Cook's distance to determine whether those outliers are actually significant. And this is our OLS regression, so our standard summary statistics. So we have an R² of just under 76%, and all of our variables apart from gender are significant. But like I said, it's hard to be able to trust this regression because of the fact that we have outliers. So what we can do is we can come up with a data frame whereby we are plotting the variables by Cook's distance. So you can see that we have a distance of 0.42, 0.24, 0.2 for the 3 highest observations, but then this drops dramatically once again as we go down the data set. And again, we're sorting based on the code, so this is just another snippet of code that allows us to sort this. And we're just seeing that we have higher Cook's distances. Now, what we're going to do to actually correct for the fact that we have outliers here is we're going to run a Huber and a bi-square regression. Now, essentially these two regressions, they're two sides of the same coin because they're both robust regressions, and we're using these to be able to place less emphasis on the outliers. So if I generate some summary statistics here, this is for the Huber weight. But what I want to show you specifically is you can see that we are generating weights for each different observation. So in this example, you can see that for the instances where usage is highest, we have the lowest weights. So it's a weight of just above 8% or so, but then it jumps to 28% when we're looking at weights more in line with the mean, and some of them have a weight of 100%. So when we generated our Huber regression, I'll just show you this again. These estimates and significance readings are actually being adjusted for the fact that there's less weight being given to the outliers. So when we run this type of regression, we can be more confident that our outliers have been reduced, or the effect of those outliers have been reduced. Now, if we generate a bi-square regression, again, these are our summary statistics. So we have our values, our significance readings. And let's see what the weights look like when we run the bi-square. So you can see that for the extreme values, we have a weight of virtually 0. So we can see that the bi-square regression is placing much less emphasis on those outliers than the Huber regression would, for example. So if you're running an analysis like this where you have significant outliers, it means that you can customize the regression to say, right, I want to place very little emphasis on the outliers, or I want to place a certain amount of emphasis on those outliers. And what we're going to do is we're going to test each of these predictions and see how each of our regressions would do. So as I said, we've trained our regressions with the training set. We're now cross-validating against the test set. So the mean squared error in terms of our accuracy, we have 70% for when we ran OLS, 76% when we ran the Huber regression, 77% when we ran the bi-square regression. So we can see that the accuracy increased when we ran the Huber and the bi-square regressions. So if we take a quick look at another data set, just to show you for contrast, and this is a data set where we don't have any particular outliers, so all our data is more or less in line with each other. So if I just generate a quick QQ plot, you can see that it's normally distributed. Practically all of our observations are on the normal distribution. And what I'm going to do is I'm going to generate the rest of the... Now, you can see that on this particular data set, we had very high levels of accuracy with OLS. So in this instance, we're not going to get any higher levels of accuracy with the Huber or the bi-square weights, but in this particular example, supposing if we had, say, 70% accuracy for OLS, if we don't have the presence of any significant outliers, it's unlikely that Huber or bi-square would make much of a difference to our predictions. In other words, we could probably expect 70% once again. So that's about outliers and how these types of anomalies can skew our results, but also how we can use weighting mechanisms to be able to correct for those. Just go back to my slides here. So again, we have our Huber by square weighting, and these are our accuracy across the regression models. Now, if we want to directly control the sensitivity of the model to outliers, we can do so using Python. So Python has a Huber regressor option using scikit-learn as well. And I'll just show you a quick example here. Supposing we want to analyze data at the 90th percentile, for example. What we're going to do is we're going to run 5 instances of Huber regressions, excuse me, but we're going to use a value called epsilon, which determines the sensitivity of the regression to outliers. So if we have a low epsilon, it's a high sensitivity, and the higher epsilon goes, the lower it gets. So I'm going to open up a Python terminal here, and I'm just going to run this chunk of code. So you can see that in terms of the deviation, as we increase the value of epsilon, our deviation is increasing, but after a certain point, it decreases. So we've seen how we can do this in R, but Python's Huber regressor command offers a little bit more flexibility in terms of being able to see, right, if we adjust the sensitivity of the regression to outliers, how will the deviation actually respond? Okay, so that covers outliers, and what I want to talk to you about now is time series shocks, how they happen and why traditional time series methods may not be sufficient in dealing with this and what we will use instead. So, quick question, anyone here from Switzerland? No one? Okay, well, the reason I asked that is because, hands up if you remember this, the Swiss National Bank, they decided to depeg the franc from the euro, and the all currencies plummeted against the franc, and some people went homeless, basically. Hands up if you remember that. Yep, perfect. So that's an example of a time series shock. It's a classic example of one because it was seen as one of the biggest movements in the currency markets in recent history. Now, if we want to be able to actually model for this, we're going to be using what's called a Kalman filter, because traditional time series models such as ARIMA don't necessarily account for the effects of this shock sufficiently. So a Kalman filter is a state space model that adjusts more quickly to shocks for a time series, and 3 particular variables that we're looking to examine is A, ATT and alpha hat, so the 1 step ahead predictions of states, the filtered estimates of the states, and also the smoothed estimates of the states. And all this means is that we're coming up with a model that is much more responsive than traditional time series models to changes in a series. So what I'll do is I'll open up our code for the Kalman filter. And what we're doing here is we're downloading data on the Swiss franc from Quandl for January 2015. And we're running a Kalman filter to see how well this model can actually adjust for the shock. So the first graph to look at is the Kalman filter, because you can see that when the shock actually happens and the dollar plunges against the franc, we can see that our estimates, our smoothed estimates, are actually moving instantaneously with the currency pair, so that when we make future predictions, we know that the shock has already been accounted for and that the future predictions are likely to be more accurate as a result. However, if we look at our ARIMA model that we run here, it's a classic 0-1-0, so there's far too much volatility for the ARIMA model to actually interpret anything meaningful. So you can see that we have a wide confidence interval here, whereas in the case of the currency pair, our estimates are adjusting to that much more quickly. So another example of the Kalman filter was when we saw Brexit. So when the pound plunged against the dollar as a result of Brexit, the Kalman filter can also be used to model an incidence like that. And the Kalman filter, as it happens, is not just used for time series. It's of great value when it comes to modeling noisy systems in general. So autonomous vehicles, for example, as an example, or computer vision applications, or any data where we generally have noisy systems or systems that are very volatile and change based on a sudden break in trend. We can use Kalman filters for that. So just before we get to the conclusion, I'll just show you a quick code of how this can work in Python as well. So there's a handy code that we can use called PyKalman, where we can obtain the smoothed state means and smoothed state covariances, because that's what a time series is essentially. We have a mean and we have a covariance, which is measuring volatility. And what the Kalman filter is doing is it's adjusting for those and it's smoothing for those. So this is a more simplistic example, but you can see that we have our state means here and our smoothed state means. So there's not too much of a difference between those series, but one is a little less volatile than the other because we've smoothed it out for it. And essentially, what the Kalman filter is doing by and large is it's taking the mean and the covariance and it's adjusting for that, so that when we run a time series and we have a sudden shock, the model adjusts that more appropriately. Okay, so to conclude the presentation, you've seen how outliers can hinder effective data analysis, but then we looked at how we can use a weighting mechanism to be able to mitigate the effects of that. We saw how we can actually screen the accuracy of those weighted regressions compared to least squares or a linear regression. And we also saw how we can use the Kalman filter to adjust for time series shocks.